Let's solve the 6 free response questions from the 2024 AP Calc AB exam. If you're looking for the BC questions, there's a link in the description. This video has chapters, so you can skip around the questions as you please. Let's begin with problem 1. The temperature of coffee in a cup at time t minutes is modeled by a decreasing differentiable function c, where c of t is measured in degrees Celsius. For t between 0 and 12, selected values of c of t are given in the table shown. Part A asks us to approximate c prime of 5 using the average rate of change of c over the interval between 3 and 7. We must also show the work that leads to our answer and include units of measure. So c prime of 5 is a derivative, which we think of as an instantaneous rate of change. We can approximate it with an average rate of change over this interval from 3 to 7. That's just the slope of a secant line. So we'll calculate the change in the temperature and divide by the change in time. So coming down here to write our work, we are approximating c prime of 5. We're using this interval from 3 to 7 because 5 is in the middle of that interval. So with the given information, this is the best we can do. So we'll calculate the average rate of change over this interval. So subtract the temperatures, 69 minus 85. That will be our numerator. 69 minus 85. That's the change in temperature. And then we just need to divide by the change in time, which is 7 minus 3. 69 minus 85 is negative 16, and 7 minus 3 is 4. So this is negative 4. The degrees, the temperature, is being measured in Celsius, and the time is in minutes. So this is negative 4 degrees Celsius per minute. That's approximately the rate at which the temperature of the coffee is changing at t equals 5. So that's part A. Let's move on to part B. Use a left Riemann sum with the 3 subintervals indicated by the data in the table to approximate the value of the integral of c of t from 0 to 12, and then interpret the meaning of that integral divided by 12 in the context of the problem. So let's begin with the left Riemann sum. Coming up to look at our table, we're supposed to use 3 subintervals, so we'll have to go from 0 to 3, from 3 to 7, and from 7 to 12. Now let's just sketch these rectangles that are making up the Riemann sum. This rectangle from 0 to 3 is going to have a height of 100, because this is a left Riemann sum, so we use the left endpoint to determine the height of the rectangle. The next rectangle has a height of 85, because that's the left endpoint. So maybe that looks something like this. That has a height of 85. And then the final rectangle has a height of 69 because that's the left endpoint at t equals 7. So maybe that looks something like this. Using this Riemann sum, adding up the areas of these 3 rectangles, we will have an approximation of the integral of c of t from 0 to 12, an approximation of the area under the curve. So coming down here to write part B, the integral from 0 to 12 of this temperature function, c of t dt, is approximately the sum of the areas of these rectangles. The first rectangle has a base length of 3 and a height of 100, so 3 times 100. The second rectangle has a base length of 4 and a height of 85, so its area is 4 times 85. The third and final rectangle has a base length of 5 and a height of 69, so its area is 5 times 69. This is part of the calculator section, so you can use your calculator to quickly find this equals 985. So that is our approximation using a left Riemann sum with 3 subintervals of this integral value. That's the approximation. But we're not done with part B, because part B also asks us to consider the integral we just approximated divided by 12. What's the meaning of that thing? Well, it's adding up the temperatures from 0 to 12, and then dividing by the length of the interval, dividing by 12. That's how you calculate average temperature. It only asks us to interpret this expression. It doesn't ask us to approximate it, though if we did want to approximate it, we could simply take 985 and divide by 12. But the interpretation is that it's the average temperature of the coffee in the cup over the interval from 0 to 12. Again, it's like adding up all the temperatures and then dividing by 12, the length of time. Moving on then to part C. For T between 12 and 20, the rate of change of the temperature of the coffee is modeled by C prime of T equals this expression, where C prime of T is measured in degrees Celsius per minute. Find the temperature of the coffee at time t equals 20 and show the setup for your calculations. So this will be pretty straightforward. We'll just take the last value we were given in our table. At t equals 12, we know the temperature is 55. And then we can use this derivative, this rate of change, to integrate and accumulate the temperature from t equals 12 up to the desired time at t equals 20. So down here for part C, what is the temperature of the coffee at time t equals 20? Well, it's going to be the time at t equals 12. So down here, what is the temperature of the coffee in the cup at time t equals 20? Well, it's going to be the temperature of the coffee at time t equals 12, which was given as 55, and then we will accumulate the rates of change from that time at t equals 12 up to the desired time at t equals 20. We're going to integrate C prime of t, which is given to us. So we'll use a graphing calculator and integrate this given derivative from t equals 12 to t equals 20. So pulling up the graphing calculator, I'll press the math button, and then I will press option 9 for the integration function. We are integrating from t equals 12 to t equals 20. And the thing we're integrating is this derivative, so we'll just be careful and type that derivative in. And rather than using the variable t, we will use the variable x, since that's most convenient on the calculator. So we're integrating this with respect to x, and we get negative 14.671. But of course, coming down to part C, we know that we also have to add 55 to this. That was the initial temperature, so to speak, at time t equals 12, which is where we started the integral. So adding 55, we get our answer of about 40.329, and that is in degrees Celsius. Finally, moving on to part D, for the model defined in part C, it can be shown that the second derivative equals this expression here. For t between 12 and 20, determine whether the temperature of the coffee is changing at a decreasing rate or at an increasing rate, and give a reason for our answer. We know that the rate of change of the temperature is described by the second derivative. So if this second derivative is positive in this interval, that means the derivative is increasing, and so the temperature would be changing at an increasing rate. If the second derivative is negative, then the first derivative is decreasing, and so the temperature of the coffee would be changing at a decreasing rate. So let's just use our graphing calculator to graph this function and see what its behavior is, positive or negative, on this interval from 12 to 20. All right, I've typed the second derivative into the graphing calculator, and here it is. We can see at a glance that the second derivative is certainly positive for t between 12 and 20. That's what the graph suggests, and looking at the function, that makes sense, because 0.2455 is positive, e to a power is always positive, 100 minus t is positive on this interval, and t squared is also positive. So yeah, second derivative is positive, so the first derivative is increasing. So since the second derivative is positive on the given interval, the temperature of the coffee is changing at an increasing rate. And that completes our solution to free response question 1 from the 2024 AP Calc AB exam. Moving on now to question 2. A particle moves along the x-axis so that its velocity at time t greater than or equal to 0 is given by this function v of t. Part A says there is one time, tr, in the interval from 0 to 2 when the particle is at rest. We are asked to find this time when the particle is at rest. And for 0 is less than t is less than the time at which the particle is at rest, we want to know if the particle is moving to the right or to the left, and to give a reason for our answer. So for the first part of this question, we're trying to find when the particle is at rest. We're just going to have to find when the velocity is equal to 0. So for part A, we will write v of t equals 0. And what value of t does this imply? Well, we can consult our graphing calculator. Typing this function into the graphing calculator and then pressing graph, we find that on the relevant interval, which is between 0 and 2, let's zoom in to that relevant interval around here, this is when the particle is at rest. There's our 0, when t, the independent variable, which is x on the calculator, is about 1.426, we'll say. So t is about 1.426. Looking at the graph again, we're not looking at this 0 over here because that's outside the interval between 0 and 2. Then for part A, we're also asked, between t equals 0 and this time when the particle is at rest, is the particle moving to the right or to the left? Looking at the graph, we can see that this velocity function is negative this entire time we can see that this velocity function is positive the entire time between 0 and this time when it is at rest. So since the velocity function is positive, the particle is moving to the right on this interval. And there's our answer. Since the velocity is positive on this interval, the particle is moving to the right. On to part B. Find the acceleration of the particle at time t equals 1.5. Show the setup for your calculations. All right, so for that, we'll just take the derivative of velocity to find the acceleration and plug in t equals 1.5. We're also asked if the speed of the particle is increasing or decreasing at this time. Speed is the absolute value of velocity, and if the acceleration and velocity have the same sign, then the speed is increasing. If the acceleration and velocity have opposite signs, then the speed is decreasing. So that's what we'll have to look at for part B. Beginning with the acceleration at time t equals 1.5, the acceleration at time t equals 1.5 is equal to the derivative of the velocity function evaluated at t equals 1.5. So let's use the graphing calculator to evaluate this derivative. I'll press the math button and then go to option 8 to access the derivative function. Rather than t on the calculator, we'll use x as our independent variable. The function is the natural log of x squared minus 4x plus 5, and then minus 0.2x. And we are evaluating this at 1.5. This is our acceleration, the derivative of velocity. We find it's about -1. So coming down here to the acceleration, we find from the calculator that the acceleration is about -1. Now, when asked if the speed is increasing or decreasing, well, we see that the acceleration is negative. I think of this as pulling the particle in the leftward direction. So if the particle's velocity is negative, the particle's moving to the left, then its speed must be increasing, because not only is it moving to the left, but it's getting pulled to the left even faster because of the negative acceleration. So then what is the sign of the velocity function at t equals 1.5? Well, going back to our graph, we can see that at time t equals 1.5, the velocity is actually negative. That's right around here when x is around 1.5 on the graph, and we see that it is negative. So the velocity and acceleration are both negative, hence the speed is increasing. And there is our answer. Since the acceleration and the velocity at this time are negative, the speed of the particle is increasing. It's moving to the left, and it's doing so at an increasingly fast rate. Moving on to part C. The position of the particle at time t is x of t, and its position at time t equals 1 is -3. We are asked to find the position of the particle at time t equals 4. To do this, we'll take the initial given position at time t equals 1 of -3, and then we will integrate the velocity, adding up those rates of change, to get us from t equals 1 to t equals 4. So for part C, we can say that x of 4 is going to equal x of 1 plus the integral from 1 to 4 of the velocity function. Now, x of 1 is given to us as -3, and for this integral, we will consult the calculator. On the calculator, I'll press the math button, and then option 9 for the integration function. We are integrating from t equals 1, because that was the starting point that we were given, to t equals 4, since that's the desired ending point. Now we'll just scroll up to the velocity function to enter it in the integral, and again, rather than t, we will use x as the independent variable on the calculator. Plugging this all in, the integral is about 0.1971. So coming back down to our work, this is -3 plus 0.1971. And so on the calculator, we will just take our answer and add -3. Doing that, we get about -2.803. And that's the position of the particle at time t equals 4. Moving on then to part D. Find the total distance traveled by the particle over the interval from 1 to 4, and show the setup for your calculations. So for this, we'll just take the integral that we just calculated, except instead of integrating the velocity, we need to integrate the absolute value of the velocity. This is because with velocity, some positive and negative velocities, like moving to the right, moving to the left, can cancel out. But since we're asked to calculate just total distance traveled and not displacement, we don't want any of the velocities to cancel out. We just want to add up all the distance traveled, so we got to integrate speed, the absolute value of velocity. So here for part D, we are going to integrate from 1 to 4 the speed function, s of t dt, which of course is the absolute value of the velocity function. So the absolute value of v of t dt. So let's go ahead and punch this into the calculator. Again, I'll press the math button and option 9 to access the integration function. We are integrating from 1 to 4. And then before I type in my velocity function, I'm going to press the math button again and then access my absolute value function, which is in the number category of that math button submenu. Option 1 is the absolute value function, and then in these absolute value bars, I can type in the velocity function. So there's the absolute value of velocity, and integrating this from 1 to 4 will give us the total distance traveled, 0.958. And there that is. The integral of the absolute value of velocity gives us this distance traveled. And that completes our solution to free response question 2 from the 2024 AP Calc AB exam. Now on to the no calculator section, beginning with question 3. The depth of seawater at a location can be modeled by the function h that satisfies the differential equation given here, where h of t is measured in feet and t is measured in hours after noon, so noon is at t equals 0. It is known that h of 0 equals 4. Part A says a portion of the slope field for the differential equation is provided. Sketch the solution curve y equals h of t through the point 0, 4, which is that initial condition that was given to us. So down here on the slope field, we will plot the point at 0, 4, or actually, it's already plotted there for us, so that's great. Now we just have to sketch the solution curve passing through this point. So sketch a curve through the point that follows the directions as indicated by the slope field. Hence, the solution curve should look something like that. So that's the solution curve for part A. Moving on to part B. For t between 0 and 5, it can be shown that h of t is greater than 1. Find the value of t between 0 and 5, at which h has a critical point. Determine whether the critical point corresponds to a relative minimum, a relative maximum, or neither. And of course, we must justify our answer. So in looking for critical points, we consult the derivative, which is given to us, dh dt. First, is there anywhere that this derivative doesn't exist? The answer to that is no. Cosine is a nice continuous function on all real numbers, and we don't know anything about the function h, which is present in its own derivative. We don't know anything about the function h that would suggest it doesn't exist somewhere either. So the derivative exists everywhere for our purpose. So then we just have to ask, where is it equal to 0? Those will be the critical points. When is this expression equal to 0? Well, h minus 1 is certainly never equal to 0 because it was given to us that h is greater than 1, at least on the relevant interval, which is between 0 and 5. H of t is greater than 1. So h minus 1 cannot be 0. Thus, the only way this derivative will be 0, and thus we get a critical point, is if cosine is 0. Cosine is 0 at pi over 2, and since the input is t over 2, this function will be 0 when t is equal to pi. That way, the input will be pi over 2. If you think back to the unit circle, that gets us up here where the x-coordinate cosine is 0. So it's at t equals pi. There are, of course, infinitely many other values of t that would make this equal to 0, but that's the only one that's in the interval between 0 and 5. So there's our reasoning written out. The only critical point on the interval is at t equals pi. Now we have to determine if this critical point is the location of a max/min or neither. To do that, we'll use a quick sign chart. Here's the critical point at t equals pi. What's the sign of the derivative to the left of t equals pi? Well, think about the unit circle. If t is between 0 and pi, then the input, t over 2, is going to be at this part of the unit circle, in the first quadrant, where the x-coordinate is positive. Thus, the derivative, seen here, will be positive, because 1/2 is positive, h minus 1 is positive, and cosine, as we just said, is positive. That's when t is between 0 and pi. Once t passes pi, the input, t over 2, passes pi over 2. And so now we're over here where x is negative. And so the sign of the derivative would be negative. Hence, the function switches from increasing to decreasing. So at t equals pi, we have a relative maximum. And there that reasoning is. There's a relative max at t equals pi because the derivative dh dt switches from positive to negative, we might say, at t equals pi. That completes part B, so let's go ahead and finish with part C. Use separation of variables to find y equals h of t, the particular solution to the differential equation that was given, with the initial condition h of 0 equals 4. So we'll take this differential equation, separate the t's and the h's, and then integrate, and then we can use the given initial condition to solve for the arbitrary constant and get our particular solution. Let's go ahead and multiply both sides by dt and divide both sides by h minus 1 in order to separate the variables. Then on the left side, we're going to have 1 over h minus 1 dh. And on the right side, we're going to have cosine of t over 2 dt. Now we can go ahead and integrate both sides. On the left, the integral of 1 over h minus 1 is just the natural log of the absolute value of h minus 1. And on the right, integrating cosine of t over 2 over 2, we're going to have sine of t over 2. If we took the derivative of this, the chain rule would give us that 1/2 that we have here. And then let's imagine that we gathered all the arbitrary constants on the right. So this is it. Now we can go ahead and use our initial condition to solve for c. That initial condition was that h of 0 is equal to 4. So plugging that information into this equation, we have the natural log of h is 4. So this is the natural log of 4 minus 1, or simply the natural log of 3. And this is equal to sine of t over 2, but we're plugging in t equals 0, so that's sine of 0 over 2, and sine of 0 over 2 is just 0. So we're really just left with the arbitrary constant c. And of course, the absolute value with the natural log, we don't need that because 3 is positive. So c is equal to the natural log of 3. So then back in this original equation where we had c, we can just go ahead and replace that c with the natural log of 3. Now we're trying to solve for h to find the particular solution. What is that function h satisfying this differential equation? So we're going to exponentiate the left and the right sides in order to get rid of that natural log. So on the left, we're going to have e to the natural log of h minus 1. And of course, the whole point is that the e and the natural log cancel out. So why don't we just go ahead and write the absolute value of h minus 1. And then on the right, we're going to have e to the power of everything that's on the right. So e to the sine of t over 2 plus the natural log of 3. But by our exponent rules, e to the sine of t over 2 plus the natural log of 3 is the same as e to the sine of t over 2 times e to the natural log of 3. But e to the natural log of 3, of course, is just 3 because e and ln cancel out. So this is just e to the sine of t over 2 times 3. So then to get rid of the absolute value, we could say that h minus 1 equals plus or minus 3 times e to the sine of t over 2. So is it the positive solution or is it the negative solution? Plus or minus? Well, we know the initial condition gave us a positive value for h. H of 0 equals 4. So in fact, this must be the positive solution. It's not plus or minus, it's just plus for this particular solution. Finally, we can add a 1 to both sides to finish solving for h. So finally, we have h equals 3 times e to the sine of t over 2 and plus 1. And if we want to go ahead and emphasize that this is a function satisfying this differential equation, we can write h of t equals this. And that completes our solution to free response question 3 from the 2024 AP Calc AB BC exam. Moving on now to question 4. The graph of the differentiable function f shown for x between -6 and 7 has a horizontal tangent at x equals -2, which we can kind of see there, and is linear for x between 0 and 7. So that's over here. It looks linear, and in fact it is. Let R be the region in the second quadrant over here, bounded by the graph of f, the vertical line x equals -6, and the x and y axes. This region R has an area of 12. Part A says the function g is defined by g of x equals the integral from 0 to x f of t dt. Find the values of g of -6, g of 4, and g of 6. The first one, g of -6, is really easy. By definition of g, well, it's the area under the function f of t, which is graphed, from 0 to whatever the input is. So if the input is -6, well, g of -6 is just the area from 0 to -6, this area here. Now, we were told the area of that region is 12, but we do have to be careful because the function g is going to calculate this area backwards, going from 0 to -6. Hence, it will actually consider this area as -12. So g of -6 is -12. All right, next up is g of 4. To calculate g of 4, we just have to calculate the area under the curve from x equals 0 to x equals 4. That's just the area of this triangle. So g of 4 is going to be 1/2 multiplied by the base of the triangle multiplied by the height of the triangle. The base of the triangle is just 4, from 0 to 4. So we will put 4 there for the base. And the height, we can see, is just 2. So our height there is 2. 1/2 times 4 times 2 is equal to 4. Finally, for g of 6, we have to do the same thing, adding up area from 0 to 6. So that's going to be the area from 0 to 4, which we already calculated. It's just 4. And then we need to add this area from 4 to 6. And we can see that's going to be a negative area because the curve is now underneath the x-axis. But again, this is just a triangle. So again, we will use 1/2 base times height. And again, we're taking all the area from 0 to 6. We already did the area from 0 to 4, so now we're just going to add the area from 4 to 6. The base of this triangle is 2 from 4 to 6, and the height we see is -1, which is why the area will be negative. So this is going to be 4 plus base, 1/2 times the base of 2 times the height of -1. So this is 4 minus 1, which is 3. That is g of 6. On to part B. For the function g defined in part A, find all values of x in the interval from 0 to 6 at which the graph of g has a critical point. And we are asked to give a reason for our answer. To find critical points of g of x, we need to consider the derivative of g of x. We know that g of x will have a critical point where its derivative is 0 or where its derivative does not exist by definition of a critical point. But we also know from the fundamental theorem of calculus, since g is the integral of f of t from t equals 0 to t equals x, the derivative of g just cancels out that integration, and so g prime of x is actually just f of x. And f of x exists on this entire interval from 0 to 6. I mean, we're looking at its graph, it certainly exists. So there's not going to be anywhere on the interval from 0 to 6 where g prime does not exist. Hence, the only places we have to look for critical points are where f of x is equal to 0. And from the graph, again focusing on the interval from 0 to 6, we see that f is equal to 0 at x equals 4. So that is our one critical point. That's the only critical point, and so that completes our solution to part B. Let's finish with C. The function h is defined by h of x equals the integral of f prime of t dt from -6 to x. Find the values of h of 6, h prime of 6, and h double prime of 6, and show the work that leads to our answers. So I'll jot down part C up here, beginning with the calculation of h of 6. H is an integral of f prime from -6 to x. So if x, the input, is 6, by the fundamental theorem of calculus, we can evaluate this integral as f of 6, so that's the antiderivative of the integrand, evaluated at this input, f of 6 minus f of the lower bound, -6, right? This is how we evaluate definite integrals. We take the antiderivative of the integrand and then evaluate it at the upper bound and the lower bound and subtract them. We can find these values from the graph. F of 6 is given as -1, and f of -6 we see as 0.5. So this is going to be -1 minus 0.5, and so the answer is -1.5. Now, what about h prime of 6? Well, the derivative just undoes the integral, so h prime of 6 is actually just going to be f prime of 6. H prime of 6 equals f prime of 6, and f prime of 6 is the slope of the line tangent to f at x equals 6. So let's look at the graph of f, and at x equals 6, we are over here. We know that this is linear, and so the derivative is just going to be the slope of this line. We can see 2 points here that allow us to quickly calculate the slope. The line goes over 2 and down 1. So that's a slope of -1/2. Hence, h prime of 6, which is f prime of 6, is -1/2. Finally, h double prime of 6, that's the rate of change of the rate of change of f, the rate of change of the derivative of f, at x equals 6. And if we look at f at x equals 6, well, we know that f is a line over here. Hence, it has a constant rate of change, and so its second derivative, the rate of change of its rate of change, must be 0. The derivative is not changing at all at x equals 6. It's a line with a slope of -1/2. And that completes our solution to free response question 4 from the 2024 AP Calc AB BC exam. Moving on now to problem 5. Consider the curve defined by the equation x squared plus 3y plus 2y squared equals 48. It can be shown that dy dx equals -2x over 3 plus 4y. Part A says there is a point on the curve near 2, 4 with x-coordinate 3. Use the line tangent to the curve at 2, 4 to approximate the y-coordinate of this point. So in order to approximate the value of the function, the y-coordinate, at x equals 3, we'll find the line tangent to the curve at this given point, 2, 4, and then we'll just plug x equals 3 into the tangent line. So for our tangent line, we will have y minus the y-coordinate, which is 4, equals the slope, and we can find the slope by plugging this point 2, 4 into the given derivative expression. So I'll just put parentheses there and we'll come back to that. The slope will be multiplied by x minus the x-coordinate, which is 2. We are just using this given point of 2, 4 to construct a tangent line, and we'll use that to approximate the y value when x equals 3. All right, now for the slope, we will plug 2, 4 into the derivative. So that's going to be negative 2 times x. X is 2. And then this is divided by 3 plus 4y. So 3 plus 4 times y, and at x equals 2, we have that y equals 4. So then just doing the evaluation here, negative 2 times 2 is negative 4, and 3 plus 4 times 4 is 19. So that is our slope. Let's go ahead and plug that in, negative 4 over 19. So here is the equation of the tangent line. We think of this as the linearization of the function at x equals 2. And it can be used to get a decent approximation of points near 2, 4. So we'll plug in x equals 3. Plugging in x equals 3 to our tangent line equation, we have y minus 4 equals negative 4 over 19, that's the slope, multiplied by x minus 2. But x is 3, so that's 3 minus 2. So then we'll add 4 to both sides, so y equals 4, and then 3 minus 2 is 1, times negative 4 over 19 is negative 4 over 19. So this is just 4 minus 4 over 19. And that is the approximate value of y, which we could combine into a single fraction if we like. Getting common denominators and subtracting, this is 72 over 19. So this is the approximate y value of the curve when x is equal to 3. Moving on to part B. Is the horizontal line y equals 1 tangent to the curve? And give a reason for our answer. If this horizontal line was tangent to the curve, then the derivative, when y equals 1, would have to be 0. If we look at the derivative and ask when it could possibly be 0, well, for this to be 0, the numerator has to be 0, and for the numerator to be 0, x has to be 0. So the slope of the curve is only 0 when x is 0. That means that if this horizontal line, y equals 1, is in fact tangent to the curve, then it must be that when y equals 1, x is equal to 0. Because when x equals 0, the slope is horizontal, or the slope is 0, so the tangent is horizontal. So let's plug in x equals 0 and y equals 1 into the equation and see if it satisfies the equation. We have x squared, which is 0 squared, plus 3y, so 3 times 1, plus 2y squared, so plus 2 times 1 squared, and this equals 48. Let's check if it actually does. If it does indeed equal 48, then yes, the horizontal line, y equals 1, is tangent to the curve. But we see, doing the math, this is 3 plus 2, which is 5, and oh, that is not equal to 48. So in fact, the point 0, 1 is not on the curve, and it's only when x equals 0 that the slope could be 0, and thus the tangent could be horizontal. Since this point isn't on the curve, it's not possible that the horizontal line, y equals 1, is tangent to the curve. So we could say the horizontal line, y equals 1, isn't tangent to the curve because the curve doesn't have a slope of 0 when y equals 1. When y equals 1, we see that x can't be 0. This point is not on the curve. And since x can't be 0, the slope can't be 0, so not a horizontal tangent. All right, let's move on to part C. The curve intersects the positive x-axis at the point root 48, 0. Is the line tangent to the curve at this point vertical? And give a reason for our answer. So we'll have to see what the slope of the curve is at this point, and if the slope is undefined, some finite number over 0, then the tangent would be vertical. So let's check. So for part C, we will plug the given point, which is root 48, 0, into this expression for the derivative, and check if it's undefined. Here's our point, here's our derivative. Let's go ahead and plug it in. dy dx equals, we're plugging the square root of 48 in for x, so in the numerator we have negative 2 times the square root of 48. And in the denominator, we have 3 plus 4 times 0. So that's just 3. And this is not infinite. This is defined, it's just some finite number. So the tangent line is not vertical because the slope is just a finite number. And thus we could say, since dy dx is not undefined at this point, the tangent line is not vertical at that point. The tangent line, in fact, has a slope of this, whatever that number equals. All right, let's go ahead and finish with part D. For time t greater than or equal to 0, a particle is moving along another curve defined by this equation. At the instant the particle is at the point 4, 2, the y-coordinate of the particle's position is decreasing at a rate of 2 units per second. So we might say that dy dt equals -2. At that instant, what is the rate of change of the x-coordinate of the particle's position with respect to time? So we're going to have to take the derivative of both sides of this equation. That's going to require implicit differentiation. We'll have some dy dt's and some dx dt's in there because x and y are both changing with respect to time. We know what dy dt is at the moment we're interested in. It's -2. And so then we'll just have to solve for dx dt. So we're interested in the instant where the particle's at the point 4, 2, and we know dy dt is -2 at that point. We're trying to find dx dt. Here is the equation of the curve. Let's go ahead and take the derivative on the left side and on the right side. On the left, we would have the derivative of y cubed, so that's 3y squared. And then don't forget the chain rule. We have to multiply also by dy dt. Y is changing with respect to time. Then for 2xy, we will need the product rule, f prime g plus g prime f. Let's say that f is 2x. So then f prime is going to be 2. Then don't forget we also have to multiply by dx dt. So 2 dx dt, that's f prime, and then multiply by g. Then we have to add g prime, that's going to be dy dt, multiplied by f, which is 2x. So dy dt times 2x. On the right, the derivative of the constant 24 is 0. Now we can plug in the known information. We'll plug in the point we're interested in, 4, 2, and we'll replace dy dt with its value at that point, which is -2. Thus, we'll have 3 times y squared, but y is 2, so y squared is 4, multiplied by dy dt, but that's -2, and then plus 2 multiplied by, let's write y first, y we know is 2, so 2 times 2, and then dx dt, which we will be solving for, and then plus dy dt, which is -2, multiplied by 2x. X is 4, so 2x is 8, and this equals 0. Then we'll move all constants over to the right side. So on the left, we'll be left with 4 times dx dt. So 4 dx over dt. And then the constants on the right, well, let's see. This is -24. So on the right, it would be positive 24. And this is -16. So on the right, it would be positive 16. So we have 24 plus 16, and that is just 40. So 4 dx dt equals 40. Thus, dividing both sides by 4, we arrive at the answer. Dx dt, the rate of change of the particle's x position with respect to time, is equal to 40 divided by 4, or 10. And if you want to include units, we were not given a unit for the distance, but we were told that t is in seconds. So we would say units per second. So 10 units per second is the final answer for part D. And that completes our solution to free response question 5 from the 2024 AP Calc AB exam. Finally, on to question 6. The functions f and g are defined by f of x equals x squared plus 2 and g of x equals x squared minus 2x as shown in the graph. So there's f of x, that's x squared plus 2, and there is g of x, that's x squared minus 2x. Part A says, let R be the region bounded by the graphs of f and g from x equals 0 to x equals 2, as shown in the graph there. Write, but do not evaluate, an integral expression that gives the area of region R. So this is just the area between two curves. From the graph, we can see that the upper function of this region, the upper bound, is f of x, and the lower bound on the region is g of x. So for part A, the area of the region R is going to be the integral from x equals 0 to x equals 2, and then we just need the area under this curve minus the area under this curve. That's going to give us this total area between them. So we're going to integrate from 0 to 2 f of x minus g of x. We could replace f of x and g of x with what they actually equal if we like, but it's also fine to leave the answer like that. On to part B. Let S be the region bounded by the graph of g and the x-axis from x equals 2 to x equals 5, as shown in the graph. That's this region here between g and the x-axis. Region S is the base of a solid. For this solid, at each x, the cross-section perpendicular to the x-axis is a rectangle with height equal to half its base in region S. We want to find the volume of the solid and show the work that leads to our answer. So the base of the solid, like it says, is this region S. And the way the solid is made is that its cross-sections perpendicular to the x-axis, so going this way, perpendicular to the x-axis, these cross-sections are rectangles, something like this. The base of the rectangle, of course, lies in the region S, and so the length of a base at a given x value would just be the corresponding y value. That would be the length of the base. The height, on the other hand, as the question says, is 1/2 of the base. So this drawing is not quite to scale, but that's how it works. Here's the base, and the height of a rectangle at any cross-section will be half the base. If I redraw the sketch a little bit more to scale, it might look like that. So this is coming out of the base S, coming out at us. This region is going from x equals 2 to x equals 5. So to find the volume of this solid, we will need to integrate from x equals 2 to x equals 5, and all we have to do is add up all of those cross-sectional areas. The area of each cross-section is just the area of the rectangles. Now, for any given x value, the base length of the rectangle, like we said, is just the corresponding y value. It's like the height of the function. And y is g of x, which is x squared minus 2x. Let's just write it as g of x for now. So that's the base length of a rectangle. And then the height of the rectangle, right? We need to multiply by the height because base times height gives us the area. The height, we were told, is just half of the base. So if the base is g of x, then the height is 1/2 g of x. So this is what we are integrating from 2 to 5. Then we can take this half out of the integral, and g of x times g of x, of course, is g of x squared. At this point, we can recognize that g of x is x squared minus 2x, and so we just have to square that, which would give us x to the 4 minus 4x cubed plus 4x squared. That's just doing x squared minus 2x times x squared minus 2x and distributing. That gets us here. Now, integrating this is straightforward. We just have to use the power rule. And it leads to this long line of calculations. X to the 4 integrates to 1/5 x to the 5, minus 4x cubed integrates to minus x to the 4, and 4x squared integrates to 4/3 x cubed. You could try taking the derivative of any of these terms and find that it gets us back to the corresponding term in the integrand. We then plug in the upper bound of 5 and subtract, plugging in the lower bound of 2. Then everything from there is just some arithmetic. And at this step, we distribute the 1/2, so the 500 becomes 250, 32 becomes 16, and so on. And then we're just left with combining the fractions, so we get a common denominator of 15, then reduce that fraction. Final answer is 414/5. Finally, finishing with part C. Write, but do not evaluate, an integral expression that gives the volume of the solid generated when region S, as described in part B, the region we were just talking about, is rotated about the horizontal line y equals 20. So let's come up to the graph and think about what this solid of revolution looks like. This says the region S is rotated about the horizontal line y equals 20. The horizontal line y equals 20 is right about there, and so we're taking this region S and revolving it about that horizontal axis. So we can sketch a reflection of this region, which would look something like this, And then the circular cross sections of the resulting solid would be washers. They'd have exteriors traced out by the x-axis revolving about the horizontal line. But then the interior would be cut out by this guy revolving about the horizontal line. So we would have a circular cross-section that looks something like this. Again, the outer part of the washer is traced out by the x-axis revolving about the horizontal line, but then the inner part is carved out by this curve revolving about the horizontal line at y equals 20. So the area of each cross-section is going to be the area of the big circle, traced by the x-axis, minus the area of the small circle, cut out by g of x. This integral will again go from 2 to 5, and what we're basically going to have is pi multiplied by the big radius squared, that's the area of the big circles, minus pi times the radius of the small circles squared. So I'll use little r for that. These are going to be in terms of x, so this would be dx. Coming up to the sketch to figure out what these radii would be, the radius of the big circle would look like this, just the distance between y equals 20 and the x-axis, which is always just 20. So the big radius, that's 20. Now what about the little radius? Well, that would look like this. It's the distance between y equals 20 and g of x. So that little radius, r, is just going to be 20 minus g of x. So then for our integral, we can take the pi out of the integral. So that's going to be pi multiplied by the integral from 2 to 5, and then we just have the difference of the radii squared. The big radius is 20 squared, and then we subtract the small radius squared. The small radius is 20 minus g of x, and this small radius needs to be squared, and that's it. This is an integral with respect to x. And we're in luck because we do not have to evaluate that, so that is the answer. And that completes our solutions to the free response section of the 2024 AP Calc AB exam. Let me know in the comments if you have any questions, and if you're looking for the BC questions, there will be a link in the description to my solutions for those. Be sure to check out my Calculus 1 course and Calculus 1 playlists, also linked in the description, and my 10 hours of AP Calc FRQs video if you're looking for a little bit more practice in the description as well. Thanks for watching.
I'm the mathematical menace, the machinations of mankind. Two calculators at the same time, hand signs and abacus, finger count and calculus. I'm a V to the T, my parameter the rapidest. Happens like this, my lecture's the most prominent, dominant. Call me De Morgan, I get the compliments. The union in together like any time that we intersect, cause my opponents know they need